Hey everyone, welcome to The Explainer. Today we're diving into a genuinely fascinating piece of research from July 2026 by Fantine Haute, Michael Kaisers, and Mirella Lapata. It's called When is Routing Meaningful? Diversity and Robustness in Language Model Societies. And let me tell you, it completely flips the script on how we evaluate multi-agent AI. If you've been tracking the space, you know everyone's rushing to string together multiple language models to chase peak performance. But this paper? It made me take a major step back and really question the hidden mechanics of these so-called language model societies. Like, are they actually doing what we think they're doing?
Think about it like building a human team. If you hire 100 people who all think exactly the same way, do you really have a functional team? Well, in the AI world, we're building these massive digital societies, routing complex queries to different agents to supposedly maximize performance. But it begs a critical question. Is your multi-model system actually diverse? Or is it just an illusion of teamwork? Are we getting genuinely unique, specialized insights, or just the exact same answer echoed back at us through different nodes?
Okay, let's dive into this. Here's our roadmap for today. First, the AI routing problem. Second, defining meaningful routing. Third, the diversity threshold. Fourth, the robustness test. And finally, when accuracy masks failure.
All right, Section 1, the AI routing problem, moving beyond just accuracy and cost.
So right now, there is a massive blind spot in how developers evaluate multimodal AI systems. Routing policies are essentially judged on just two things: task accuracy and inference cost. Basically, did it get the right answer and how cheap was it to run? And sure, those are absolutely crucial, but relying only on them creates this massive illusion of success. An AI system can score off the charts on task accuracy and stay super cheap to run, while literally failing completely at being a functioning, specialized multi-agent society.
Because here's the thing, a system can hit high accuracy while totally failing to specialize. The researchers highlight two ways this goes wrong. First, you can have a redundant society. This is where you have a pool of agents all basically doing the exact same thing, totally violating the idea of diversity. Or you get inconsistent assignment, where queries are just handed out seemingly at random, which destroys stability. In both of these cases, true specialization is completely blocked, no matter how good the system looks on those basic accuracy leaderboards.
Which brings us to Section 2, defining meaningful routing. What makes an AI team actually effective?
If accuracy and cost aren't the whole story, what is? Well, the researchers propose a fix by defining two critical properties that are entirely separate from basic performance metrics. The first pillar is behavioral differentiation. Simply put, your society of AI actors actually has to act differently from one another. If you ask 5 different models a question and all 5 give you the exact same identical response, that entire routing process is totally vacuous. It's pointless. True diversity in how these models behave is non-negotiable if you want a multi-agent system to actually work.
The second pillar they introduce is routing stability. This means if you take a query and just slightly tweak how it's phrased, a surface form variant, the routing policy should still consistently assign it to the same specific actor. A minor wording change shouldn't cause the AI manager to freak out and route the task to a completely different agent. If it does, the system isn't stable. The routing isn't based on any deep understanding of the task, it's just blindly reacting to superficial text changes.
Moving on to Section 3, the diversity threshold. How many models do you actually need?
To actually measure this stuff, the researchers adapted a metric from complex systems theory called hierarchic social entropy, or HSE. They ran this on language model societies using benchmarks like EmbedLLM and RouterBench, and they discovered a frankly shocking truth about the whole "let's just throw more models at the problem" trend. It turns out HSE exhibits massive diminishing returns. Sure, adding a second or third model brings in a lot of fresh diversity, but as you keep piling on more and more models, the amount of unique, new behavior you get just drops right off a cliff.
So here is the crucial point. The data points to a very specific threshold: fewer than 10 models. A carefully curated subset, a practical core set heuristic as they call it, of fewer than 10 AI agents recovers almost all the available diversity you could ever squeeze out of a massive pool of models. You literally do not need a society of 50 or 100 models. If you curate your team right, fewer than 10 is the sweet spot. That's a real game changer for anyone trying to build meaningful AI systems without burning through a mountain of compute.
That leads us to Section 4, the robustness test, surviving the perturbation test.
Now, to test that second property, stability, they built a brand new perturbation-based robustness metric to diagnose those hidden failure modes we mentioned earlier. It's essentially a stress test, and it works in 2 steps. Step 1, introduce a surface form variant of a query.
Step 2, track the router to see if it maintains consistent actor assignment. Basically, does it send the rephrased query to the same specialist, or does it completely lose the plot and send it somewhere else?
And finally, Section 5, when accuracy masks failure. Not all routers are created equal.
The researchers unleashed this exact stress test on different types of routers, and it brilliantly illustrates the danger we've been talking about. When you compare a CAN-N router to prompted routing, standard accuracy metrics make the CAN-N router look incredible. It actually gains accuracy when using specialist societies. But under the perturbation stress test, the CAN-N router totally collapses. It completely falls apart just because a prompt was slightly rephrased. Meanwhile, prompted routing remains totally stable across all those different perturbation types.
To really tie the whole shebang together, there's this profound quote straight from the researchers. Accuracy and meaningfulness can sharply diverge. A KNN router might look like an absolute rock star on paper, making you think you've built this hyper-intelligent, highly efficient system. But that accuracy is just a mask. In reality, the routing isn't meaningful at all. It's brittle, it's unstable, and it crumbles the second it hits a slight variation. Looking good on a benchmark is absolutely not the same thing as being a truly functional, robust system.
Which leaves us with this final, provocative thought. If the AI systems crushing our accuracy leaderboards today are actually brittle, redundant, and completely lacking true diversity under the hood, are we measuring AI success entirely wrong? As the whole industry pushes for bigger societies and higher benchmark scores, this research is a huge wake-up call. A genuinely intelligent system isn't just about blurting out the right answer. It's about having a meaningful, robust, and diverse process for getting there. Thanks for joining me for this explainer, and we will catch you next time.